Episode 70, titled Iteration Loops, From Constraints to Experiments to Better Outcomes, the goal is to iterate systematically so improvements are real, not random, because modeling progress is often an illusion when changes are not controlled and results are not comparable. The exam cares because it tests process discipline, not just technical vocabulary, and disciplined iteration is what separates reliable improvement from lucky fluctuations. In real systems, iteration is constrained by time, compute, and operational risk, so you need a loop that respects constraints while still producing meaningful learning. The central theme is that iteration is an experiment design problem. You propose a change, measure its impact under consistent conditions, and decide whether the change is worth keeping. If you do not control the loop, you end up overfitting to your own validation set, chasing noise with confidence, and creating a model you cannot maintain. A systematic loop makes progress measurable and keeps stakeholders trusting the direction of travel. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Iteration begins with constraints, because constraints define what improvements are feasible and what trade-offs matter, even if a model could score higher in an unconstrained environment. Time constraints determine whether you can run extensive experiments or need quick wins, and budget constraints determine whether you can add data sources, purchase tooling, or run expensive training workloads. Compute constraints determine which model families and feature pipelines are realistic, and latency constraints determine whether a model can be deployed in an operational workflow without slowing systems or decisions. Risk constraints include privacy, compliance, and safety concerns, because some experiments are not permissible even if they improve metrics. The exam expects you to recognize that a best model in the abstract can be unacceptable in the real environment if it violates constraints, and the correct answers usually align model choices with operational limits. When you set constraints early, you reduce wasted work and prevent later rework when stakeholders reject a solution for reasons you could have anticipated. With constraints clear, you create a hypothesis and change one thing at a time, because controlled changes are the only way to attribute improvements to a specific intervention. A good hypothesis is specific, such as adding a particular feature family, adjusting a sampling strategy, or switching to a model type that matches observed nonlinearity, and it includes an expected direction of impact. Changing one thing means you keep data, splits, metrics, and pipeline constant while altering only the targeted element, so you can interpret differences as evidence rather than as confounded noise. The exam cares because uncontrolled experimentation produces ambiguous results, and scenario questions often test whether you can design a clean comparison rather than stack multiple changes and claim success. This discipline also makes iteration efficient because when an experiment fails, you know exactly what failed and you can learn from it. When you treat iteration as hypothesis testing, you convert tuning into learning. To keep results comparable over time, you must track experiments consistently, because iteration is only useful when you can trust that the comparisons are fair. Consistent tracking means recording the data version, feature set, pre-processing steps, model type, hyperparameters, random seeds where relevant, and evaluation design for each run. It also means using a consistent naming scheme so you can reconstruct the experiment tree and understand which changes were tried and in what order. The exam may not ask for tooling, but it does test whether you understand that reproducibility is part of valid experimentation, because without it, you cannot confidently claim progress. Consistency also prevents selective memory, where only the best result is remembered and the failures that reveal the true difficulty are forgotten. When you track experiments well, you build an evidence trail that supports both internal learning and external stakeholder confidence. Validation discipline is central because without it, iteration loops can become self-deception, especially when you repeatedly look at outcomes and make choices based on noisy fluctuations. Proper use of validation sets means you use training data to fit models, validation data to compare alternatives and tune decisions, and a final holdout test set to estimate true performance only after you have committed to a model design. Avoiding peeking into test outcomes is critical because every look influences decisions, and once the test set influences your choices, it stops being an honest proxy for future performance. The exam often frames this as avoiding leakage or maintaining an untouched test set, and the correct reasoning is that evaluation integrity depends on separation. Validation also includes choosing a split strategy that matches reality, such as time-aware splits for time-dependent processes, because the wrong split can make the validation score meaningless. When you guard validation integrity, you protect your loop from producing inflated performance claims. Hyperparameter tuning should be done with discipline because endless searching can become a noisy fishing expedition that overfits validation rather than improving the underlying model design. Discipline means setting a reasonable search space based on model understanding, limiting the number of trials, and prioritizing changes that are likely to matter rather than exploring arbitrary combinations. It also means using validation results to learn about sensitivity, such as whether performance is stable across a range of settings, because stability is often more valuable than a single best score. The exam expects you to recognize that hyperparameters are not magic knobs that always rescue weak signal or poor features, and that tuning cannot compensate for bad labels, leakage, or missing key drivers. A disciplined tuning approach also respects constraints, because the cost of tuning must be justified by expected returns in performance and stability. When you tune with discipline, you treat tuning as an evidence-driven refinement step, not as a substitute for good feature and data design. Selecting the best model is rarely about a single metric, and the exam frequently tests whether you can choose based on metric, stability, interpretability, and cost together rather than chasing the highest score blindly. Metric performance must match the objective, such as ranking quality for prioritization or calibrated probabilities for threshold decisions, because the wrong metric can produce a high score that does not translate into operational value. Stability matters because a model that swings across retrains or segments cannot be trusted for consistent decisions, even if its average score is high. Interpretability matters when governance and stakeholder trust require explanation, because opaque models can be rejected or misused without clear understanding. Cost matters because a model that requires expensive compute, complex pipelines, or heavy maintenance may not be sustainable, especially when improvements are marginal. The exam expects you to weigh these factors explicitly because real-world success is multidimensional. When you choose a model with this lens, you demonstrate that you can optimize for decision quality, not just leaderboard metrics. Repeated trial and error can lead to overfitting to validation, which is a subtle but common failure mode where the model appears to improve, but only because you have implicitly optimized to the validation set's quirks. This can happen even when you keep the test set untouched, because the validation set becomes a target through repeated selection. The symptoms include diminishing returns, fragile improvements that disappear on new splits, and model choices that seem to work only under a particular window or random seed. The exam cares because it tests whether you understand that validation is not infinite evidence and that repeated selection changes the meaning of validation performance. A practical response is to use stronger evaluation design, such as cross-validation or multiple time windows, and to reserve a truly final holdout for confirmation. Another response is to reduce degrees of freedom by narrowing the search space and focusing on mechanism-driven changes. When you recognize validation overfitting, you stop trusting small gains and start demanding robustness. Knowing when to stop iterating and ship is a judgment skill, and the exam often probes it through scenarios where performance gains are small or costs are rising. A model is ready to ship when it meets minimum performance requirements on appropriate held-out evaluation, is stable across key segments and time periods, satisfies interpretability and governance constraints, and fits operational cost and latency limits. It is also ready when the marginal improvement from further iteration is outweighed by the opportunity cost and risk of delay, especially when monitoring and retraining can support post-deployment refinement. Stopping does not mean perfection. It means you have enough evidence that the model improves decisions relative to baseline and that it can be maintained safely. The exam expects you to recognize that endless iteration can be worse than shipping a good enough model, because delays can prevent real value from being realized. When you can articulate ship criteria, you demonstrate that you understand modeling as an operational product rather than a perpetual experiment. Communication of trade-offs is essential because iteration decisions involve performance gain versus complexity and maintenance, and stakeholders need clarity on what they are buying with each new layer of sophistication. A small metric gain might be worthwhile if it reduces false positives substantially, or it might be not worth it if it doubles infrastructure cost and complicates governance. Complexity also increases risk because more features and pipelines mean more failure points, more drift exposure, and more debugging burden when performance changes. The exam expects you to communicate these trade-offs plainly because decision-makers must choose how much complexity they are willing to maintain in exchange for incremental performance. Clear communication also prevents misalignment, where stakeholders assume each iteration guarantees improvement, while the reality is that improvements are uncertain and must be tested. When you communicate trade-offs well, you turn iteration into an informed investment process rather than a technical black box. Documentation must stay updated throughout iteration because data versions, code, and settings are part of the model, and without them, you cannot reproduce results or explain why a change helped or hurt. Documentation includes dataset snapshots, pre-processing steps, feature definitions, hyperparameter settings, evaluation splits, and decision rationale for why one model was selected over another. The exam treats this as governance and auditability because a deployed model must be defensible, and defensibility requires traceability. Documentation also supports team continuity because iteration often spans months and multiple people, and memory alone is not reliable. When documentation is current, you can roll back, compare, and diagnose with confidence instead of rerunning experiments from scratch. Maintaining documentation is not overhead. It is what makes iteration cumulative rather than repetitive. Monitoring should be planned early because iteration continues after deployment in practice, and the deployment environment is where drift, feedback loops, and real operational constraints reveal themselves. Monitoring includes tracking input distributions, performance metrics, calibration, and segment disparities, because those are early signals that the model's assumptions are breaking or that the environment has shifted. Planning monitoring early ensures you have instrumentation, thresholds, and response playbooks in place before the model goes live, rather than scrambling after issues appear. The exam expects you to treat deployment as part of the modeling lifecycle, not as the endpoint, because models degrade when the world changes and because iteration is ongoing maintenance. Monitoring also informs the next iteration cycle by providing real-world error cases and evidence about where the model struggles, which is often more valuable than another round of offline tuning. When you plan monitoring up front, you make iteration a closed loop from evidence to improvement rather than a one-way push into production. A helpful anchor memory is change, measure, learn, then decide and document. Change means you alter one targeted element based on a hypothesis and constraints. Measure means you evaluate under consistent, leakage-resistant design with appropriate metrics and stability checks. Learn means you interpret results, including failures, to understand what the evidence suggests about signal, assumptions, and next steps. Decide and document means you choose whether to keep the change, ship, or iterate again, and you record the outcome so the team's knowledge accumulates. The exam rewards this anchor because it captures the core of systematic iteration, which is controlled experimentation with traceable outcomes. When you use this anchor, you avoid the common trap of making many changes and hoping for improvement without understanding causality within your own workflow. This anchor turns iteration into a disciplined scientific process. To conclude episode 70, outline one iteration cycle and then choose a stop rule, because this demonstrates you can operate the loop responsibly. A clean cycle begins by confirming constraints, such as latency limits and privacy requirements, then proposing a single hypothesis, like adding a rate-based feature family to normalize exposure differences. You would implement only that change, keep the evaluation split and metrics fixed, and compare performance, calibration, and stability to the previous version and to baseline under held-out validation. You would then review error patterns to see whether the change improved the segments and cases that matter operationally, and you would record the configuration and results so the comparison remains auditable. A practical stop rule is to stop iterating when two consecutive, well-designed experiments fail to produce a stable improvement beyond a defined minimum threshold that justifies added complexity, because at that point, the loop is likely chasing noise rather than signal. You would then ship the best stable model that meets constraints and plan monitoring to guide future iterations based on real-world evidence. This is the disciplined outcome. Iteration is systematic, bounded by evidence, and aligned to constraints, so improvement is earned rather than assumed. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.